Alright guys, I'm actually recording, so okay. Process of finding a derivative is called differentiation. Just so you know. So we're going to be finding the derivative. We've talked about that before. We found the derivative already for slope of point tendency. F prime, right? Yes. We've done that. That was D2. So now we're just going to get to the nitty-gritty of, now you know what a derivative is. Now we're going to get to the nitty-gritty of solving that a lot faster than doing a big table of values. But you guys have done this a million times, so it's not that big of a deal. So I'm going to show you the formal proof. So we know k being a constant, so the derivative of a constant function. So you guys remember this from last time? The limit as h approaches 0, and that is f of x plus h. Subtract f of x all over h. You guys remember that? Yeah. Okay, so let's talk about a constant function. If I have f of x equals 2, what kind of graph does that look like? Straight line, right? Horizontal, right? So that means for any x value, y is going to be 2. So it's going to look like that, right? You guys with me so far? You kind of have to have an idea of what it looks like for what I'm about to do. So what is the f of x? So it's x plus h. It doesn't really matter what that h value is. What's my y value always going to be? 2, right? So this is going to have the exact same value as this. Because if x is 7, and this is 7.00001, we know the y value is always going to be 2. Does that make sense for everybody? Because it's a constant function. It doesn't matter where x is. So as h approaches 0, we know that we're going to have k minus k, that's a k, over h. So what's that? So the limit as h approaches 0 is going to be 0 over h. Is that undefined? Is that indeterminate? Not yet. If you evaluate this, what does it give you? 0. So we know that the limit of a constant function is going to be equal to what? Or the derivative of a constant function, I guess I should say, is 0. So the derivative of a constant function is going to equal 0. Are you ready for this? That looks like a lot of words. It's not really that bad. All it's saying is that if you have a function where you have an exponent, the exponent gets moved out to the front, and you subtract the original exponent by 1. So if the original function was, let's say, x cubed, your derivative, so this is, stop doing a lot of math, your derivative is going to be this. So f prime of x. The exponent gets moved to the coefficient, so this is going to be 3x. Going back to here, you subtract that by 1. That's my derivative. No. Good try. So I'll prove it to you, but this is how derivatives of powers work. So let's do this one. Let's do the one I gave you. Okay, so the limit as h approaches 0, so it's going to be f of x plus, I don't want to do cubed. Can I change my mind? Can I do this one? Can I do it squared? I can do that faster in my head. Is everybody okay with that if I prove that one? Okay, based on the rule, what would be my derivative? What happens to the exponent? Moves out front to become a coefficient, and the exponent changes from a 2 to a 1. So if my original function is x squared, my derivative is 2x. Okay, I'm going to prove that to you now. I just don't want to cube something. Okay, so if I were to expand this, this would be x plus h squared for the y value. So this would be x squared plus 2xh plus h squared minus x squared all over h. We did this before. Proven this one before, I think. So the x squareds go away. The limit as h approaches 0. So I'm going to common factor in h because we've seen this magic before. What happens to the h's? They divide out, they equal 1. So we're finding the limit as h approaches 0 of 2x plus h. Do direct substitution, what do you get? 2x. So this is going to equal 2x. If we do direct substitution, h equals 0. So you can use your derivative rules to not do all this math. Okay, are you okay? You look upset. I thought this would be a good day, like where you don't have to do this math anymore. Okay. So let's do some practicing. So the original function is f of x to the exponent 4. So when I'm doing the derivative, what happens first? The exponent moves to the coefficient, and then the exponent is reduced by way easier than doing all that math to prove it. You can use your given laws, your given rules, to just go ahead and do this. If you feel like proving it using limits, go ahead. All right, so we're going to differentiate this one. So because it's given as y, we're not going to, I would write it as y prime. I would do f of x prime because it's given to me in a form where it's y prime. So what happens? What's my coefficient? A third. So proud of you guys. And then I have my variable. It would be an x. I just wanted to use a different variable. It's really more fun. Look. Okay. So now the question is, what's my exponent? For those of us a little slow on the uptake, because some of us need to see all the steps, which is me. So I'm subtracting 1 from my exponent. So 1 and 3 over 3 minus 3 over 3 gives me my negative 2/3. This would be, I'm going to say, where I marked your test. Some people lost some really big chunks of marks for transcription errors or silly math mistakes. Like it should have been 2 times 3 and they put 2 times 2. Or it was x plus 2, x minus 2, And he canceled with minus 2s, but then when you broke it down, it was still x minus 2. So things like that, transcription errors, so this is really easy to mess up. All right, so now you're going to go back to your grade 9 exponent rules. Grade 9. I wouldn't leave it like this. I would write it like this. That becomes way easier to see of what the exponent is. Now, when I do my derivative, that's a really easy one to mess up too. -3 happens a lot. And the last one, you have to write it as a rational exponent, because your knowledge of radicals versus rational exponents. So I rewrite my original function as x to the exponent 1/2. So now I know my derivative is 1/2 x to the -1/2. If you were to put that back in radical form, what would it look like? Just for funsies, let's do it. Okay, what's the negative? Tell me about the x. It's on the denominator, right? So 1's on top, 2's already on the denominator. My x is moved to the denominator, but an exponent of 1/2 means what? The reason why it's not bad to do this practice back and forth, because if I gave you something like this as your original function, you've got to put it into that notation in order to do your derivative. That's great. Awesome. Perfect. Whew. Oh. I don't want it. Do I have to? Okay. It's a cube. I don't want to. So all it's saying is if you have a function that has a constant time, like if you have a numerical coefficient, sorry, for your derivative, it's going to be your derivative function times by that constant again. Ready to prove it? So let's just do this. Let's say, so what would f prime of x be? Okay, what happens to that coefficient of 4? It stays outside, and now you do the derivative. So do the derivative of just the x cubed. So what is it? So what's your derivative? Okay, now I'm going to show you the painful math that goes behind that. It's something why I'm never going to do it again now that I know the class rule. All right, here we go. All right, so we have our limit as h approaches 0 of f of x plus h minus f of x all over h. Okay. So now, I'm going to do this as a side note. I have to find f of x plus h for 4x cubed. So this would mean that it's going to be 4 times x plus h cubed, which means 4 times x plus h times x plus h times x plus h. Did I mention I want to cry? I'm going to do these two first because I can do those really quickly in my head. Okay, So I'm going to go x, so that would be x cubed plus 2x squared h plus xh squared plus x squared h plus 2xh squared plus h cubed. Got it? What? Who's that? Did I screw something up there? Yeah, you totally good. I'm doing it old school, so let me have my moment, okay? So I can add these, I can add with that, so I'm going to have 4 times x cubed, x cubed plus 3x squared h. I can combine these two, which gives me plus 3xh squared plus h cubed. Oh yeah, and I gotta multiply that forward. I don't know why you guys don't want to do it the long way all the time. Okay. My arm is sore. A lot. So going back to my limits, I'm switching colors from I'm tired of purple. Limit as h approaches 0. So we're going to have 4x cubed plus 12x squared h plus 12x h squared plus 4h cubed minus 4x all over. Those go away, right? Those cancel each other out. I'm going to factor out an h. I'm skipping some steps here, folks. I'm skipping some steps. So I'm going to have 12x squared plus 12xh plus h squared. I divided an h into here, an h into here, and an h into there. I think I did it all right. I missed? What did I miss? Oh, I missed a 4. See? You guys are so smart. Okay, if I do direct substitution, what am I left with? Do it in your head, easy peasy, right? I will say the rules are way easier. I mean, if you want to prove it long way, you can. I will ask you to do something silly like this so that you can achieve D2 outcome. So I know you can do it the long way, but D3 you can apply it to. All right, bottom of the page. Differentiate that, please, and thank you. You know what I'm telling? It's disappointing. Everybody get that? Perfect. Easy peasy. Okay. So nothing too crazy here, but a little bit. So all it's saying is that if you have two functions in here, so both of these have variables, like it's a multiple term polynomial, you are going to do the differentiation of the first one added to the differentiation of the second one. You have to treat them as kind of two separates and then add them back together. Pretty easy, nothing crazy. So I would do F. Let me break this down. This is all it's saying. Feel free not to break it down like that. It's saying y is equal to f of x plus g of x. So f of x would equal the 2x cubed, and g of x would equal the 4x to the exponent 4. That's all it's saying in that little box up there. It's just saying it's breaking them down into two separate functions. Easy enough to do. I wouldn't break them down and do them separately. If you want to, you can. But for this one, it would be 2 bracket 3x squared plus. So I differentiated the first one, and now I'm going to differentiate the second one. So the 4 stays up here, times 4x cubed. So I'm going to have 6x squared plus 16x cubed. Yeah. Wait. I'm waiting. I'm waiting. Can I go now? Yes, I'm good. Oh, okay. I was waiting. I didn't know what I was doing. So that's all it's saying up there. You can treat, if you have something with multiple x's in it, treat it like they're two different functions. This is a nice one to give you, only because I'm asking you to change forms. Really, the only thing you have to do is change this one first. So I have y equals 3x to the exponent 4 minus 5x squared plus 2 times x to the negative 1/2. I think some people might forget the negative. I don't think the 1/2 would trip you up. I think the negative moving it from the denominator to the numerator can trip you up. So now if we differentiate it, really easy peasy. So y prime so this the big thing will be is the signs here. So negative 12x to the negative 5. That one's nice and easy. There's nothing tricky about that one. Nothing really tricky about the second one. This one, things get a little trickier. The 2 divides into the 2 once, but you have a negative 1, so it's going to change to a subtract. Subtract 1x. I'm just going to write subtract x to the negative 3 over 2. If you write add, then I expect your next term to be in brackets. So that's it. Doing differentiation using the rules, so much faster. And then we're going to use the rules to differentiate second and third levels as well. So what does your first